Now in this section we are going to evaluate the surface area of a curve which is rotated across both x and y axis, right? So let's first take the case where it is rotated across the x-axis. Here we start with a curve in the xy plane, right? And we can name that curve in this notation, right? Y is expressed as a function of x, right? And then what we do is we rotate that curve across the x-axis. Now keep in mind that we are this board that I am writing is in the 2D space, okay? And if something comes out from this 2D space, it will form a three-dimensional object. In other words, it is situated in the 3D space, right? So simply, if this line is rotated across the x-axis, then this line must come to the three-dimensional space, right? And it will form a certain solid object. I have an animation with me. I can show it to you. Right. Now see this diagram. Here we have this line, right? Now this is a line, something very similar to the one that I drew, right? And see what will happen if we rotate it across the x-axis. Here, see, it will slowly form a three-dimensional object. Okay, it will form a three-dimensional object when it is rotated across the x-axis, right? See, upon rotation, now this object on the right hand side is in the 3D space, right? It's some sort of a tangible object, right? And our goal is to compute the surface area of that three-dimensional object. Okay, so in this three-dimensional object you have a certain surface area in here. See, all this area is in a 3D space, and our goal is to compute that surface area, right? Now to compute the surface area, we have some equations derived with the help of integration. Now here in this course I am not going to do the derivations, but like what we are focusing mainly is on the calculations by using these formulas, right? Okay, so when it comes to the formula for the area of this surface, you should understand it clearly, okay? And we have to remember, we have to keep those formulas in our mind, okay? Right. Then now when it comes to the formulas, before writing down the formulas, I have to tell one more thing. Now we obtained this diagram or this solid object by the rotation of a curve across the x-axis, okay? But you should understand that we can rotate the same curve across the y-axis as well, and if it is rotated across the y-axis, it will form a different object in the 3D space, and again we can find the surface area of that particular 3D object, okay? Right, so depending on the axis of rotation, you have two different formulas. And for the formula for the x-axis rotation, what I mean by the formula is the formula for the surface area. Okay, surface area. And for the x-axis, the formula is S is equal to 2 pi y ds. I'll explain these terms with an example also. And for the y-axis rotations, you have a very similar formula but with a slight difference. Here you have x. See, if it is x-axis, you have y here. If it is y-axis, you have x here. And there's a way that you can remember those, like which goes to which axis. Now this is a way only to remember this formula. Okay, this is not the derivation. One way to remember is like, now when it comes to this case, we obtain this by x-axis rotations, right? Now what I mean by x-axis is x-axis rotations, and this is the y-axis rotation, right? So if it is rotated across the x-axis, you can see that it forms a circle like this. Okay, it will form a circle like this, right? And there in that circle, you have the y coordinate as the radius of that circle. Now I am telling you a method to memorize those two things, right? This is just a method. This is not the derivation of this equation. Okay, now you can see if it is an x-axis rotation, you have a circle like this, and to compute the circumference of this circle, we will need 2 pi r, and for r you have the particular y coordinate at this position, right? Because that coordinate will represent the radius of this circle at this instant, right? So we have this 2 pi y term, right? But it was a x-axis rotation. Okay, so like that you can remember this formula, because if you write 2 pi x for the x-axis rotation, then it is wrong. Okay, right. And this ds term is also a special term, right? Remember, in previous video we did the formula for arc length, right, which is this one, dt. And remember, for this f prime t, there were two options. One is dy by dx and the other one is dx by dy, right? A very similar thing is there for this term also. Now this ds represents two things. ds represents two things, that is, it can either be this one, dy by dx squared dx, and here you have a square root. This is the almost the same thing as it was in the arc length formula, because we in the derivation we are using the arc length formula, that's the reason. And the other one is dx dy squared dy, right? So you can use any of these two options for both x-axis rotations as well as for y-axis rotation. So the only difference is, if it is a y-axis rotation, you have x here. If it is a x-axis rotation, you have y here. And for ds, you can use this one or this one for both x and y axis rotations. But sometimes it will be easy to compute this one, and sometimes it will be easy to compute this one. So depending on that, we will have to choose one out of these two options, but sometimes both options may be less complicated, right? I mean easy. Right, and in the next video I will go over some examples to illustrate this idea.